year in the making, this talk, I think. We kept inviting him and he kept saying no, but now we finally have him on the hook and he's here. He did his PhD in Oxford with Marshall Penrose, so he's an Oxford man. But nowadays he's gone over to the dark side, I'm afraid, and he's coming just from Cambridge today. But he'll be talking about something that's been interested with this for a long time, which is classical simulation of quantum computation.
Well, great, thank you very much. And pleasure to have this opportunity to visit Oxford again. Okay, so I'm going to talk about classical simulation of quantum computations. And this is a very interesting topic because classical simulation is in fact a very useful and mathematically precise tool for studying the relationship between quantum and classical computing and complexity, and also other related issues which are often very kind of loosely formulated, sort of issues such as, you know, what are the essential quantum features or quantum resources that might make quantum computing better than classical computing and so on. So in particular we can study the classical simulation complexity of restricted classes of quantum circuits, as we'll see later on as we go through, and this provides a way of exploring the relationship both from above and below in a certain sense. So for example, we can seek classes of quantum circuits or quantum computations that are hard to simulate classically, that can't be efficiently simulated classically. And hardness issues in complexity theory are always notoriously difficult. So we're usually satisfied in this situation with proving something slightly different, mainly that an efficient classical simulation of a certain kind of quantum computation would imply some implausible collapse of classical complexity classes, like it would imply P equals NP or something like that. But also on the other side, like from below in a sense, we can seek classes of quantum computations that are classically efficiently simulatable. So in that sense, they're computationally lame. They don't offer computing power for us. But on the other hand, they can involve very rich quantum effects and still shed light on this issue of what makes quantum computing work. And in particular, given such a class that doesn't give you extra computing power, you can ask what extra quantum resource do you need to throw in order to regain universal quantum computing power. And it's in that sense, that can be claimed to be a kind of essential resource relative to this background of sort of not effective quantum processes. So we get all this interesting, rich interplay between classical and quantum theory. Okay, so to start then, I'd like to say a little bit more about what we mean by classical simulation of a quantum circuit. I guess I'm going to assume in this talk some basic knowledge of quantum computing and things, which hopefully many people will have. So the issue here is that you're given a description, you're given a quantum computation described as a quantum circuit, which is just a list of quantum gates and the lines on which they act, and you're given its input, which is usually a computational basis state described by a bit string of length n, or a product state we'll consider as well, a quantum state that's a product state of n qubits, and you're told which output lines you measure for the output of the computation. So you could have one line for a decision problem, but maybe more lines, in more general cases for more outputs. And this is all classical. So this is just a great big long bit string, and if capital N is the size of the circuit, the number of gates, then this is up to logarithmic factors. This is kind of linear in the size of the circuit, because each gate needs some finite amount of stuff to describe it, and the line numbers are logarithmic in the number of lines and so on, the description of them. So you're given all that, and we'll always be interested in circuits that are polynomial in the number of qubit lines. so you think of capital N as polynomial in little n. So this description, this classical description, is a kind of polynomial length in the number of cubic lines. Okay, so having got this classical description of quantum computation, we want to simulate it by purely classical means, not by running the quantum process itself. And there are various notions of simulation you could ask for, and broadly there's weak and strong, at least we'll introduce these terms. And a weak simulation is, given this description, you want to provide a sample of the output distribution that the quantum process would produce by classical means, with a classical computer and classical random numbers. But a strong simulation is sort of stronger in the sense that we want to do more. We want to calculate a value for the output probability distribution. So then you could sample it afterwards if you like. If you have many lines, we want to calculate the output distributions or any marginal of them, any one of those in polynomial, given the description here. So I guess we include marginals here because we want strong simulation to imply weak simulation. So if you can compute all the probabilities efficiently, and there would be exponentially many of them if they're at kind of order and output lines, then you still can't sample that distribution necessarily. But there's a trick to do that, a way of doing that, if you can also compute the margins. But I don't want to digress and describe that here. So we have these two things, and then we're mostly interested in efficient simulations. So we want to either sample or calculate the probabilities in classical polynomial time in little n or capital N. Okay, so and if there's a precision issue with calculating probabilities, we require it to be polynomial in the number of digits we calculate them to as well. But that won't feature in what I'm going to say. It won't really cause any problems, so I won't kind of sort of talk about precision issues. So notice that the quantum process itself, if you run it, only gives you a sample of the output distribution. It doesn't provide you with value of the probabilities. So weak simulation, weak efficient simulation is really the most relevant thing of interest, and it's what the circuit actually gives, it's the quantum process. And so if you have a weak efficient simulation, then that means the quantum process provides you with no computational benefit. But in this talk, I'll talk mostly about strong simulation, about techniques for computing probabilities in certain situations, because a lot more is known about that, and there are some interesting results, and perhaps at the end I'll make some more remarks about weak simulations. Okay, so I want to begin by describing a kind of standard case study that's well known, the so-called Clifford computations, and these are a well-known class of classically, strongly, efficiently simulatable quantum computations. But even though they've been around for a long time, they still have the ability to generate interesting new insights and results, as I hope to kind of convince you as we go along. So just to define what these Clifford gates are, these quantum gates, we have the standard Pauli group on one qubit generated by the standard X and Z and the identity 2x2 matrices there, the unitary operators. And then we have the n qubit Pauli group on n qubits. It's just a tensor product of n copies of this group. So it's a finite group of order about 4 to the n. And a Clifford operation on n qubits, on all the qubit lines, is defined to be any unitary operation which preserves this n qubit Pauli group under conjugation. So like this. So if you like, in group theoretic terms, it's the normalizer of this group in the group U, unitary group in dimension 2 to the n. So you just have this here. So, okay, so these are going to be our gates of interest. And they have this very special kind of algebraic property which we'll exploit in simulation situations. So, and it's known exactly what these things are. A unitary operation is a Clifford in this sense, if and only if it can be written as a circuit of the 1-qubit Hadamard gate, the phase gate with one I, and the control Z gate. So I'll assume you know what they are. And furthermore, given any such basic Clifford gate, one of these sort of generating ones, if you conjugate a Pauli product, you can easily compute the update rule as to what the new Pauli matrices are, the tilde ones on the other side, given this. So that will be also significant. You can compute them in poly and time very easily. Okay, so we'll consider eventually, in this first example, simulating Clifford circuits of these 1-qubit and 2-qubit gate with some extra ingredients, which we'll come to in a moment. But before then, I want to just indicate how we can actually strongly simulate just standard circuits of these Clifford gates of, say, polynomial size and number of qubits, and we allow our input state to be an arbitrary product state here, and the output we'll measure a single line, say the first line, without loss of generality, and let P0 and P1 be the probabilities of measuring 0 and 1 at the end of that quantum process for some Clifford circuit C. So there's a standard, so this is usually known as the Gottesman-Knill theorem. It's a variant of the original version, which is slightly different and was proved in a completely different way as well. But this theorem now admits an extremely simple proof, which I want to kind of go through because we'll see that there's interesting ways of generalizing this idea later on to provide other classes of circuits that are simulatable in a strong sense. According to just the basic rules of quantum mechanics, the projector onto 0 of a qubit is the identity plus z over 2, where z is the Pauli operator. And the probability of seeing 0 is simply the expectation value of that in the final state of the process of the circuit. And the final state is the circuit applied to the input state, which is general product state here. So if you plug that in here, so the identity just commutes and the C's annihilate each other, so you get a half, you get 1 from the identity, and then you get this expression here with Z1 being Z on the first line and identities on all the remaining lines. And because our circuit is made up of Clifford operations, and this Z1 is one of these Pauli products, it's one of these guys with Z here and identities everywhere else, whenever we conjugate it by the gates successively of our circuit, we can figure out what the updates are, and then doing that polynomially many times to get the complete circuit C, we can compute this expression to be the input state and a tensor product here of these Pauli matrices. And now, since the input state is a product state, this potentially exponentially big calculation, so this is a matrix of size 2 to the n by 2 to the n, and this is a 2 to the n dimensional vector, but everything falls apart because of the product structure, and it just collapses down to a product of n 2 by 2 matrix calculations, and hence you can compute all that in polynomial time. So we can compute all this in polynomial time, and hence compute the probability of 0 and similarly 1 for any given Clifford circuit. And so this is a complete proof of this theorem. Much simpler. The original proof by Gottesman-Knill, this Clifford operations initially came out of the theory of quantum error correction, and they had a different kind of stabilizer formalism approach, which need in this talk, and they effectively compute a description of the evolving state through the computation. Whereas here we don't even have that. We kind of propagate the final measurement back to the start. Roughly speaking, we kind of do the opposite. So this is much, much simpler than the original proof, and applies to a slightly different situation as well. Okay, so this has been known for a long time, since the early 1990s or thereabouts, or at least a different version of this. And everyone just thinks that Clifford circuits are always just classically simulatable. But as soon as we start allowing with extra ingredients, everything becomes much more interesting. So extra ingredients I'm going to sort of mention in some combinations, not all possible ones. But so instead of measuring one output line, you might consider measuring many output lines. And the output probability distribution is on many bits now. So there's that choice there, or you can restrict your inputs to be computational basis states rather than general product states, so it's a more special case. Does that help in various situations? And perhaps most interestingly, you can allow single qubit measurements within the circuit as the circuit's going along, and subsequent gates after you make the measurements can be chosen either non-adaptively or adaptively depending on the measurement outcome. So you get these kind of adaptive circuits where you measure a qubit along the way and then possibly choose the subsequent gates in one or other way depending on whether the measurement gave 0 or 1. So, and then a fourth thing which I don't list here is strong versus weak simulation complexity. And recently with Martin van der Nest, we sort of investigated the simulation complexity of all 16 combinations of these choices with weak and strong as well. And there's kind of some interesting ingredients there. So I just want to kind of highlight a couple of the results of that, just to indicate how interesting the situation can get when you do this. And I don't want to sort of give detailed proofs necessarily. So here's a first theorem, for example, to indicate a kind of delicate relation between the simulation complexity and what you're allowed to do. So suppose you have Clifford circuits just as before, exactly the same situation, input states, product states, and you don't do any measurements along the way, but you measure many output lines. Okay, so now the output is a probability distribution over order n bit strings rather than just a single bit. Then if you do that, you kind of think about, well, what's that going to do? Well, if you try and do the same trick as here, if you want to compute the probability that a whole lot of things come out to be 0, then you need to put these projectors in for all the separate bits. So if you have order n bits, you have order n of these I plus z terms here. And when you multiply them all out, you get exponentially many terms in this calculation. So this method of proof is not going to work anymore if you just simply measure more output lines. However, those exponential sums, it turns out, can still be computed in classical polynomial time because they turn out to have a special form. And if in the case that the input's restricted to computational basis rather than general product states. So we can prove this result, and it's quite a lengthy proof. It takes sort of 2 pages to write out this proof. That if the inputs are computational basis states and you measure many lines, then the simulation is still possible. A strong classical efficient simulation is still possible. However, if the inputs are just allowed to be general product states now instead of computational basis states, the strong classical simulation now becomes sharp P hard, which would be very, very hard, much harder than NP complete. And it's not too hard to see that, but things I'll say later on sort of indicate how that comes about. So this is kind of an interesting thing. It indicates that the intuition we gain about the failure of this proof is wrong, because you can still patch this up if the inputs are computational basis states, but not if the inputs are arbitrary product states. So it indicates a kind of subtlety of this distinction between things that seem to be fairly close. So that's just a kind of starter. But the one that's perhaps most interesting, I think, that I want to try and communicate what this means, or what this implies, which is a little bit unsettling for people who like to think quantum computing is more powerful. So suppose we now have Clifford circuits with product state inputs, and we're back to our single line output case. So that's all strongly simulatable. But now we're going to allow intermediate measurements as well. And in the case of non-adaptive circuits, where you just make the measurements, but subsequent gates are not chosen according to the outcomes of the measurements, then strong classical simulation is still possible in polytime efficiently. But if you now simply allow your subsequent circuit gates to be chosen adaptively according to the measurement outcomes, then strong classical simulation now becomes sharply hard again. And this is even now with computational basis inputs, not even with general product state inputs. But if you allow product state inputs as well, and adaptive circuits in this scenario with Clifford circuits, then it becomes universal for quantum computing. Namely, within those resources, you're able to represent an arbitrary quantum circuit. So that's kind of interesting. So these are not very hard to prove, so let me just indicate how these things come about. So the thing is, if the circuit is non-adaptive, where you don't choose subsequent gates, depending on the outcome of the measurement, then non-adaptive circuits are essentially equivalent to circuits where you don't do any measurements at all, and this just reverts back to the previous theorem. So the idea very simply is, if you've done some unitary gates, U here, and you measure a qubit line, and I should have drawn more lines going through here, so you measure this one line, and then you do some more gates over here, but you don't choose them according to what happened here. Well, this is exactly equivalent to doing a controlled X, a controlled knock onto an ancilla, an extra qubit line that kind of decoheres this line, if you like. It reduces it to a probabilistic mixture that you get in the measurement, and then you don't use this anymore. You throw that away and you carry on. So these two things are exactly the same, and this extra gate we've introduced is a Clifford gate. It's actually one of the Clifford gates. So this bigger circuit is still a Clifford circuit, but it's got no measurements in it, and hence we can just simulate that.
So the basis that you measure in, is it a Pauli basis?
No, it's always, when I say measurement, it's always a computational basis status. It's not even, I mean, you could do a Pauli measurement by applying a Pauli's before you measure, but when I say measurement, I only mean 0, 1 basis, you know. So yeah, always. So to prove, so this is kind of interesting here, and this actually can imply that. Basically the reason this happens is, you can sort of understand that intuitively. If you have adaptive gates, then you have the controlled NOT gate as a Clifford gate. So if you're allowed to have it adaptive, then you can have a controlled NOT gate as well. You can control the application of this based on the value of another line, if it's 0 or 1. And that controlled NOT gate is the Toffoli gate, which is universal for classical computing. So basically, even with computational basis inputs here, you can apply the Toffoli gate to standard basis states in a classical sense. And with the Hadamard gate, you can have random numbers. So within these resources with computational basis inputs, you have universal classical probabilistic computing. And if you can compute probabilities, then that's sharp P hard because you can just run a classical computation which evaluates a Boolean function or a randomly chosen input, and the probability that you see 1 for the value is exactly the information of how many satisfying assignments there are. So, so hence you can compute that within these resources. But anyhow, I think it's most interesting to look at 2 here, and to see how that works. We exploit another known theorem that the Clifford gates, together with this one qubit gate, which is the square root of the 1i, the phase gate that we already had in the Cliffords. This is the square root of that. I called that one S, this one's called T. So if you throw that in as well, then that's all universal for quantum computing. You could make arbitrary quantum computations out of this. So all we have to do is be able to apply this gate T on any line, and then together with Clifford's we can make arbitrary quantum computing. So what we do is we take this state called pi over 4, which is simply 0 plus the relevant phase times 1, and we have that as an extra ancilla line here. So that just extends the product state input. So it's just another qubit there. And it's a short calculation shows that if you take any qubit line and do a controlled X operation from that line onto this state, and then you measure this state here, you get the answer 0 or 1, then that will apply either T or its inverse, T inverse to this green line. So that's just a simple calculation. And we want T, so if B was 0, we get T. If B was 1, we get T inverse. So to turn T inverse back into a T, we multiply by T squared, which is S. So here's our adaptation. We measure that to get 0 or 1, and we apply the Clifford S gate to the power of whatever this was. That's our adaptive choice, and then that will effectively apply this gate T to this line. So, and this control X and this S gate are Clifford's, so this whole thing is a Clifford circuit, but it's an adaptive choice. We choose the gate depending on the result of this measurement. So hence we get universal quantum computing, and then we expect also, I guess most people would expect that efficient weak simulation is unlikely too now, because that would mean all of quantum computing can be simulated, which we don't think is the case. So that's an interesting result, and I want to kind of just emphasize what this says, because if you hadn't seen it before, you probably didn't follow all those ingredients, but it has a very striking and rather unnerving implication if you just understand what's actually being said here. So what we've got, Clifford circuits, product state input, single line output, and we're allowing intermediate measurements. If you have non-adaptive such circuits, that's efficiently simulatable. In the strong sense, so also in the weak sense, such circuits have no computing power beyond the classical. Right? They can be simulated with polynomial overhead with classical circuits. But on the other hand, if you simply adapt your circuits, it becomes QC hard. In other words, it has full universal quantum computing power. So just to emphasize these two things, so here's the kind of structure. If you introduce the symbol MIY to mean measure the ith qubit line, and the result comes out to be y, which is 0 or 1, then in A, so you apply some Clifford gates, which I just call C0, so the green C's here are just some Clifford circuits, and then you make a measurement, and then in a non-adaptive case, you just apply another Clifford circuit, and then make another measurement, another Clifford circuit. But in the adaptive case, you do your circuit, you do your measurement, and then you choose your next circuit depending on, you can choose it to be one or other of two things, depending what you've got here. And then you make another measurement, and that circuit can be a function of all the previous measurements. So we're contrasting these two situations. And A has no computing power, even though it's a quantum process beyond the classical, whereas B is fully universal for quantum computing. So so it's interesting now to note that B has an extra ingredient to A, which is this adaptation, which is a purely classical ingredient. So here, all the power of quantum computing comes from a purely classical source. But it's even worse than that. The quantum processes you get out of B are exactly the same as the ones you get out of A. You don't get any new processes here, because any adaptive circuit that comes out here could well have just arisen as a non-adaptive one, which just happened to be chosen in this way. So, in the sense of quantum processes, there are no new quantum processes introduced by doing B rather than A, and even worse, if experimentally there's no difference at all between these two situations. So suppose you're a theorist and you're telling an experimentalist in his lab what to do, and he can do Clifford things and measurement, so you tell him, well, do a Hadamard on the 5th qubit, then do a controlled knot, measure the 4th line and tell me the result. You know, so it does it. And then, now do a Hadamard on the 7th line, now do this. Measure the 1st qubit and tell me the result. Now, the experimentalist cannot possibly know whether you're choosing the subsequent gates adaptively or not, because anything you tell him to do could have arisen non-adaptively. You can't possibly tell. Yet, in one case you have classically simulatable computation, and in the other case you have fully quantum universal computation. So, so this is a rather bizarre situation about, and kind of is rather curious as, in its relation to the question of where the power of quantum computing comes from, because here we don't even use any new processes, we simply use the same ones, but we kind of mix them in a classical probabilistic way. So that's a rather unnerving sort of little observation. Okay, so let me move on now. So that indicates that, you know, even these good old Clifford circuits still have interesting things to say if you consider them just in very slightly enlarged environments, adding in extra ingredients. So that kind of inspires us to look for other interesting, you know, are there other interesting classes of quantum circuits that can be classically simulated but still have rich quantum effects? And there are such known things, and I want to describe now a method, a kind of mathematical method for arriving at such things. So I want to kind of generalize the ingredients of how this Clifford simulation works. So, you know, you have to think back to this proof now, this thing here. Why did this work? It was, you know, it was because we could compute the update of these product operators in polynomial time. The description of these operators is only polynomially big in n, even though they're operators in 2 to the n dimensions, and we could compute these expectation values here because breakdown in product. So if you kind of isolate all these things that you want, so the key features I kind of list here as these 3 simulation criteria. So we have this restricted class of qubits, of gates, which are the Clifford gates, which have the crucial property that they preserve some structure, which is the Pauli group, which has sort of polynomial limitations on its complexity. So I say poly-sized, I should really mean polynomially complex. So the issue here is that any element of the Pauli group can be described in polynomial-sized terms, in contrast to a general unitary operation on n qubits, which is exponential in its description. So we have these gates which preserve this polynomially limited structure, and furthermore the update under conjugation of the new elements you get is computable in polynomial time. So we want that, and furthermore, for elements of this structure, which is the Pauli group, the expectation values should match the input states, so they were product states and product operators. So we want that to be computable in polynomial time. And finally, our structure should contain interesting quantum observables like Z on the first line or projection operators in order that these guys can be used to compute probabilities. So we want to kind of mimic these three situations, and we seek other kind of mathematical examples of where this arises. This kind of where something stays only polynomially complicated in a potentially ambient, exponentially complicated environment of further things. And recently I realized or discovered a way of doing this using some simple theory of Lie groups and Lie algebras, only to find shortly thereafter that it had already been described some years ago in a paper by Sommer, Barnum, Ortiz and Knill in 2006, but this paper appears to have gone by completely unnoticed, and as far as I can tell, even people who are most interested in simulation issues weren't aware of this result either. I mean, it's just that it's written in such a way that it's kind of encrypted in pure mathematical terms, and begins by lots of complicated Lie algebra theory, which most people are not familiar with. So I'd like to kind of try and explain to you how this works now, and how it leads to another interesting class of simulatable things, just automatically from this theory, which turns out to be Valiant's theory of matchgates and holographic algorithms. So it can be understood in a completely different way from Valiant's motivation from this point of view. Okay, so let's start talking about Lie algebras. So I don't even need abstract Lie algebras. I just want finite dimensional matrix. So Lie algebras are going to be matrices already. So a Lie algebra is a vector space of matrices, so closed under linear combinations, and it's a Lie algebra when it's closed under the bracket operation, which is simply defined to be the matrix, commutator X, the matrix product two ways around. So we don't even need the abstract definition of bilinear, antisymmetric, and Jacobi identity. So this is very explicit. But we'll be interested in so if you have a basis for this vector space of matrices B1, so it's d-dimensional, then the structure constants which characterize the structure of the algebra are simply tell you how to form the bracket of the basis matrices, and hence of all linear combinations. So these are these constants C with these three indices characterize the abstract structure of this Lie algebra, and we will later be interested in other matrix representations of this algebra where you have another set of matrices, perhaps bigger ones, and with a basis, and you map this basis onto that basis, and it preserves these computation relations with the same structure constants. So two algebras with the same structure constants are isomorphic in this sense. So associated to a Lie algebra, you have a Lie group, and normally you start with the Lie group and come back to the Lie algebra, but here, since we're being so explicit, you can go the other way. Given a matrix, or given the matrices in the Lie algebra A, you can consider their exponentials, where the exponential is just the usual power series of matrix powers. So this is another bunch of matrices, and they form a Lie group. And the fundamental, or one of the first results about the theory of representations of Lie groups is that there's this so-called fundamental adjoint representation where the Lie group acts on a vector space by linear maps, and its Lie algebra, the vector space given by its Lie algebra, provides this fundamental representation of the Lie group. So whenever you have a Lie group, so just think of all these as matrices, if you act on its Lie algebra by conjugation, so here's e to the x and here's its inverse, so we conjugate the matrices by these exponentiated matrices, then that forms a representation of the Lie group, and in particular for us, it means that the Lie algebra is preserved under this conjugation. And this is this is very similar to what we have in our first simulation requirement. So the Lie algebra here the Pauli group is what's being generalized to be a Lie algebra, and the Clifford gates are now the Lie group, which act on this algebra by conjugation and preserve. So that's precisely what that adjoint representation theorem says. But then we don't just want any Lie algebra Lie group, we want to kind of have all these polynomial constraints happening as well. So in particular, we'll have input product states often, so we will like our Lie algebra to be made up of product matrices again, tensor products of n 2 by 2 things, and have all these properties. And furthermore, this adjoint representation update rule of the Lie algebra should be computable in suitable polynomial time. And we get that, that also comes from general Lie algebra theory, is that the adjoint action, this conjugation action of exponentials of the Lie algebra on the Lie algebra itself can be computed in polynomial time in the dimension of the Lie algebra. So in particular, given a basis of the Lie algebra and a general element x, which is a linear combination of the basis, we want to know what happens to the basis element under conjugation by this general element in the Lie group. And so we want to know what these aij's are. And there's a standard calculation to do this. And I guess we don't really need to go through this, but it's not very hard, as you can see. There's a complete derivation here. And the bottom line is that to compute what these aij's are, which is essentially this conjugation action, all you need to do is exponentiate a matrix, where the matrix M here is obtained from the structure constants of the Lie algebra, which you know, and the coefficients of the thing you're conjugating by e to the x. So if you look at this matrix here and exponentiate it, that computes these numbers that you're after. And standard arithmetic and matrix multiplication is all doable in polynomial time, so in the size of the matrices, and hence you can compute this exponential by summing the series to enough terms so that you can get order d digits in polynomial d time. Okay, so one can easily do that. So coming back to our simulation now, for n-qubit lines, so the idea now is that the Lie algebra is like the Pauli group, and the Lie group, the exponential, the e to the x's, are the gates that our quantum circuit is going to be made from. So they're like the Clifford gates. So we associate a Lie algebra, which I call a sub n, for n-qubit lines, of dimension that's polynomial in the number of lines, and we represent it by matrices of size 2 to the n by 2 to the n. So in other words, by matrices that act on the space of quantum states of n qubits. And then we have our first simulation requirement, because, for example, the update rule can be computed in poly d time, and d was polynomial in the number of lines as well by our choice of the algebra dimension. And so therefore the circuits that we're going to be able to simulate are made up by exponentials of these things. But for quantum mechanics, we want our gates to be unitary. So if the thing we're exponentiating in a Lie algebra is skew Hermitian, then the exponential will be unitary. Okay? So skew Hermitian means the adjoint is minus the minus x. So then we'll get unitary gates, which is what we want. And for the other two simulation requirements, we just need a suitably nice choice of these matrices that we're using here, like product matrices or so on. So now we can start playing this game and looking for particularly algebras and representations by matrices, of which a lot is known. So in particular, if you choose the Lie algebra to be the the Lie algebra of the rotation group in 2n real dimensions, which has polynomial dimension 2n squared minus z. So these are skewed. These are kind of the infinitesimal versions of rotation, so they're skewed matrices of size 2n by 2n. And then we choose a suitable representation of this Lie algebra, not its basic 2n by 2n matrices, but as bigger matrices of size 2 to the n by 2 to the n, which are product matrices. If we choose that correctly, then the whole formalism we've just developed turns into Valiant's theory of matchgate computations, and it provides a totally different way of approaching this. So, Valiant's theory provides this novel method of obtaining new classical polytime algorithms, and he introduced it via the theory of counting perfect matchings in graphs, as he does a lot with. Like for planar graphs and so on, these can be counted in, this can be computed in polynomial time. And Valiant's theory became interesting for quantum computing because it implies the classical strong simulation of a special class of quantum computations, these so-called matchgate ones. And you can see how this works explicitly with a little bit more algebra. And then you get a little bit more at the end, which is kind of interesting. So in order to get Valiant's result, we sort of step back a little bit first. So we want a representation, what these matrices whose commutation relations are the same as the thing you get from rotations in dimension 2n. And these can be generated from so-called Clifford algebras. So this is the same Clifford, but this is not related to the Clifford gates before. So the same person doing two different things, coincidentally, that we're interested in. So we start with a Clifford algebra now, which is on 2n generators, which is simply the algebra generated by these generators which anti-commute. So before we were talking about commutation for Lie algebras, but now these are anti-commuting with a plus sign in the middle. Okay, so it's quite different. And so these objects anti-commute and they square to the identity. If mu equals mu, you get the identity. And then you look at all products of these in linear combinations, you get a 2 to the power 2n dimensional algebra of all these combinations where you sum over all products based on all subsets of 2n things. So that's why it's 2 to the 2n dimensional. And then you look at this thing and you notice that the linear span of all these things that satisfy these anti-commutation relations are not closed under commutators. So they don't form a Lie algebra. For example, the commutator is c nu minus that, which since they anti-commute then, is just two lots of that. So a commutator is a quadratic term, and hence it's not in the linear span. But on the other hand, if you look at quadratic terms instead of linear terms, the set of all quadratic terms is easily seen to actually be a Lie algebra. It's closed under commutation, curiously, by virtue of the anti-commutation relations up here. So that's sort of easy to check. The commutator is simply defined to be the difference of the products the two ways around. And so you get a Lie algebra out of this, a particular Lie algebra with some structure constants, and one can show that this Lie algebra is in fact isomorphic to the Lie algebra of rotations in dimension 2n. So that's kind of a mathematical fact. So that's the Lie algebra we're going to associate. So this is a nice Lie algebra that comes from these Clifford algebras, which is not a Lie algebra. Then we associate this to n-qubit lines, and we want a nice matrix representation of it with product matrices. So there's a well-known such thing as well from both physics and mathematics, the so-called Jordan-Wigner representation. So here it is, with each of the n-qubit lines, you associate these two operators where for the kth line you put the x and the z Pauli operators there. You put all z's to the left and identities to the right, and you tensor product them all together. So I've left out all the tensor product signs. So you get these 2n operators, these c's, acting on n qubits, and they're Hermitian as well, and they actually anti-commute. So this really does give you a representation of the Clifford algebra conditions that we had before. And since they're Hermitian and anti-commute, it's easy to see that sums of quadratic terms with real coefficients and an I here are skew Hermitian, so exponentials of those, which are going to be in the algebra, are unitary. So these, we're going to use these as our unitary gates for our, so these are like the Clifford gates, and the quadratic span of these C's is like the Pauli group. And also the Z operator on the kth line is easily seen to be in our Lie algebra. It's just simply expressible as a quadratic term in these things. And so hence we can just plug all this in, and it follows from that simple basic result of Lie algebras and Lie groups that if we're given any circuit, quantum circuit of unitary gates of this form, where the C's are these guys, and the output measurement is the measurement on the kth qubit line, you know, any one of the qubit lines, then the output can be classically strongly simulated in polynomial time. So we get this simulation result with these non-trivial sort of gates here as well. And it happens to correspond almost exactly with Valiant sort of results. So it's sort of interesting then to just be a little bit more explicit about what these gates are. You know, so we can actually compute what they really look like because we have all these explicit matrices. And if you take the quadratic terms just from two nearest neighbouring lines, like these two and these two, and take general linear combinations and compute this exponential, it's not very hard to see after a little bit of calculation that you get 2 qubit gates that act on those 2 qubit lines, and they always have this special form where the 4 corners, A, B, C, D, and the middle are populated, and you have zeros elsewhere, and the 2 matrices you get from these sub bits of these 4x4 matrix are both in SU2. So you get anything like this up to an overall phase. And so what happens with more general quadratic terms? Well, you can also show that if you don't just take the 4 C's that come from nearest neighbour lines, consecutive lines, k and k plus 1, but just general ones over all the lines, then any such unitary can be expressed as a polynomial size circuit of these gates. So in a sense, these generate everything anyhow. They don't leave anything out in a sense. And in fact, a cubic size circuit of these gates. And ultimately, this just boils down to a statement about rotations that you know, rotations in some number of dimensions can be expressed in terms of Euler angles, which are rotations in two-dimensional, a sequence of two-dimensional rotations. So that kind of is how this decomposition works at the end of the day. And if the 4, if you use 4 of these C's that are not from consecutive lines but distant lines, then the corresponding exponent, the exponential unitary gate you get, acts over all the intermediate lines, not just those 2 qubit gates. So this gives a completely different sort of approach to how Valiant's theory works. But Valiant's theory also allows some further gates that we haven't got yet. So this was slightly mysterious for a while, and Valiant noticed this as well, that his theory of match gates allows further unitary gates that are not expressible as exponents of these quadratic terms in this formalism. So the question is, where do they come from and how do they fit in? So in particular, notably, Valiant was allowed not only to have these 2 qubit gates that we've just described, but he could also apply arbitrary 1-qubit gates, but only on the first qubit line, and still classically simulate those, whereas we can't do that. And from our point of view, from the physics point of view, the fermion physics interpretation of these match gates, it's a very unnatural extension. It violates basic physical principles to allow these sorts of gates, but you can still do it mathematically, and it still works. And so the issue is how can that happen? Well, it turns out that the Lie algebra formalism can easily extend to incorporate that, because we've already mentioned that the span of the linear terms is not a Lie algebra, but the span of the quadratic Clifford algebra generators is a Lie algebra. And then we note that the span of both linear and quadratics together is also a Lie algebra. So, you know, before we noticed that the linear terms are not closed because that commutator is a quadratic term. However, if you lump quadratic and linear terms together, they give you a slightly bigger Lie algebra than the one we've been looking at, and in fact it's isomorphic to rotations in one extra dimension, Sn squared plus 1. So now our Lie algebra formalism just immediately generalizes that the Lie group can not only have exponents of quadratic terms, but you're allowed to have linear terms as well, and you can still simulate, you know, classes of circuits of these gates. So in particular, on the first, so in this sums now, we can have x on the first line, y on the first line, which are just the first two generators, the linear ones here, and the z on the first line is essentially the product of those two. So in this exponent, we can now have arbitrary combinations of x, y, and z on the first line, and that amounts to having arbitrary 1-qubit gates on the first line. So our formalism can indeed incorporate, it seems, all the things that Valiant got to, and it seems that this approach provides a totally complete description or proof, different kind of proof of Valiant's result from his original formulation. Okay, so this is just meant to illustrate that this Lie algebra formalism can lead to interesting new results, although that one was already known. So to finish in just a few more minutes, I just wanted to sort of mention a further issue is, so we've been talking about strong simulations and computing probabilities because that's more amenable to interesting mathematical developments, but in fact we should really be interested in weak simulation. Remember, weak simulation is where, given a description of the quantum circuit, we want to produce a sample of its output rather than the value of a probability, because after all, this is what the quantum process itself gives you. And if you're interested in simulating the output of the quantum process, it's this you should ask for, and not hugely more, which is the probabilities. And so far we've had interesting computations that can be strongly simulated, so in fact weakly simulated too. So that's sort of interesting, sort of non-trivial ones, the Clifford ones and Valiant's matchgate circuits. And we had evidence that some quantum computations cannot be strongly simulated, so that a sharp P hard. But on the other hand, that's sort of maybe interesting, but not really interesting for us, because it may be the case that strong simulation is sharp P hard. It's still possible that weak simulation can be done in polytime, you know, so it's this we're really interested in, not this. And you know, there are trivial examples of this. If you just take classical polytime probabilistic computation, then clearly strong simulation of that is sharp P hard, because you just take a classical computation that evaluates a Boolean function on a random input, and the probability that the value is 1 is essentially measures how many ones there are. So that's a sharp P hard problem. Whereas such computations are weakly simulatable by themselves. You know, a polytime classical computation is a weak simulation of itself. Right? So it's kind of trivial, and so this doesn't really cut much ice with us. So what we would really like, and not assuming initially that quantum computing is better than classical computing, say for bounded error probabilistic computation, we want evidence that some quantum computations can't be weakly simulated rather than strongly simulated. So for example, a weak simulation implying some implausible collapse like sharp p equals p or np equals p or something. So, and it's sort of interesting that very little is known about this. So I just want to just quickly quote one result here, which is a result of mine with Nick Bremner and Dan Shepard a couple of years ago, is in fact you can get very, very simple quantum computations. You start with all zeros, you apply some Hadamard gates, so the state here is nothing more than a uniform superposition of all n-bit strings, and then you apply a circuit of diagonal, purely diagonal qubit gates, and the diagonal entries, which are phases to be unitary, need only be multiples of pi over 8 with the phases here, so not even complicated diagonal gates. So they don't do anything, they just put phases in front of here. So if you measure that, you've done absolutely nothing, because they just go out with probabilities. But then you just all you do is you re-interfere them with another layer of Hadamard gates and kind of interferes them all together, and then you measure some lines here. And then the theorem is that if you measure a number of lines that's order n, quite a lot of lines, then efficient weak classical simulation of this process would imply that the classical polynomial hierarchy collapses to its third level. So that's what we're able to prove. So without saying anything about what this is, that's usually regarded as implausible. It's not the same as p, not even p equals np, but you know, most people would regard that with horror, I think, if that happened. But on the other hand, if you don't measure too many lines, if k is only logarithmic in n, so if you measure just a constant number or logarithmically many lines, then a weak classical simulation is possible, an efficient one. So it's crucial, it depends on the large number of lines. So this appears to be exactly the kind of result we want, evidence that quantum computing really is more powerful than classical computing, which could still be in doubt, I think. However, there are some shortcomings which make this result not as good as it appears at first sight. So just to quickly mention these, the method of proof for that result fails if we allow any additive error in the simulation, in the weak simulation. So in other words, this result holds only if you simulate, the weak classical simulation simulates the probabilities exactly, or up to a multiplicative error, but not an additive error. And physically this is bad because probabilities can generally be exponentially small, so a multiplicative error would imply an exponentially high precision, which we don't like to accept. So what we really want is some version of this theorem where you can tolerate a small additive error in the probabilities rather than wanting them exactly or multiplicatively accurate. And that's not known, and people are still working on that. Here in particular, and it may be possible, but we don't know. And another shortcoming of this result is that it relies on measuring many output lines. So it's a sampling problem of this strange probability distribution that's the issue here, and it's not known how to relate this to any actual computational task of interest. It's just sampling this thing. Is there some interesting actual computational task which has an algorithm that requires you to sample this mysterious distribution along the way and then perform the task, and hence can't be classically simulated unless this polynomial hierarchy collapses. So this theorem, unfortunately, still is not quite what we want, because what we really want is we want a weak simulation that the collapse still applies if the simulation is inaccurate with some small additive error. But no such thing is known as far as I know. And And that would be a really important thing to establish here. And that would finally give a firm feeling that quantum computing really is more powerful. You know, everyone always says you can factor in polynomial time in a quantum computer, but a lot of people believe that it's just a matter of time before there's a classical efficient factoring algorithm, right? So for example, in the bounded error context, in which that algorithm operates, it's not at all clear whether you can't classically simulate any quantum computation. So, although most people think not. So, a result of this kind would sort of seal that. So that's something people are desperately trying to sort of do at the moment, and that's a rather urgent issue. So I've run a little bit out of time, sorry about that, and so perhaps I'll stop there. Thank you.
Any questions? John?
Well, I was just wondering if you could say anything about the disposal sampling problem that people have talked about, and how it relates just to this last.
Yeah,
So
I guess
some results about.
Yeah, it's a kind of physical version of this. I guess Scott Aronson's boson sampling result, and it uses a different class of circuits here with the same kind of conclusion, and they're circuits that relate directly to things you could do in linear optics in quantum optics labs. So, but he again has this problem of multiplicative approximations.
So it's the same shortcoming.
Yeah, exactly the same shortcoming, and he has these complicated conjectures about permanence of certain kinds of matrices and stuff, which would resolve his problem, but it just seems to be a much more complicated version of the situation. Really.
So. You mentioned this nice abstract criterion for generating these things that can be classically simulated. Do you have other candidates besides these Lie algebras that fit that criteria?
Not really. You don't even have to have that. You can sort of generalize as much as you like, and you don't need a group or a vector space or anything in the middle there. But so you just want to look in mathematics around for things that, if you just sit down and want to invent a set of things which are invariant under conjugation by something, it's not that easy to do. And this Lie algebra thing is a natural mathematical example, but it's hard to invent such things which are not trivial, to have a non-trivial sort of normalizing thing on the other side. Basically anywhere in mathematics where something grows polynomially, where it did grow exponentially, then you just want to kind of get a unitary representation of that and convert it to something that, I don't really know about any other good candidates.
Can you go back to your first example where you had measurements and feed forward?
The Clifford thing.
Yes, because I wasn't paying quite enough attention there, as one
This
doesn't.
one? You
Well,
mean
not
this
quite
one?
that far. Where you had the diagram of the circuit and you states measurements there.
This one, yeah.
So I wasn't paying enough attention as to what actually got measured. Single qubits at a time?
Yeah, you measure single qubits always in computational basis state. And,
Right.
yeah.
Yes, because I was conflating that with an actual circuit diagram and how much was measured. Is there a limit on how many you measure at once? Are you allowed to measure only one at each?
Well, it depends. Well, you can do whatever you like. You can make
But
up
if
your
you
own.
measure
But
all of them,
yeah, well, that's obviously.
that's what I'm saying. There has to be some. I think
Yeah, if you measure them all, you're just throwing away your content.
Right, exactly. So there has to be some limit in there.
Yeah.
What
So
it
the
was.
point is, in order to get this universal computing power, it suffices to measure only one at each time. And
Right.
furthermore, the adaptation is utterly trivial. It's not a complicated adaptive circuit. It's only ever this.
Right, yes.
Which is
Now,
very,
that
very
bit
simple.
I understand because
Yeah.
it's very like measurement based. But I was
Yeah,
then
yeah.
thinking, but if you measured all of them, you haven't got anything. So
Yeah,
where's what
But you don't have to measure them all. I mean,
No, I know you don't, but I'm wondering what the limit is.
you mean you want to measure as many as possible?
Yes, how many can you measure and still have and it still give you something powerful.
Yeah.
Is that?
I guess it depends on the structure of the circuit. But also in this, we're allowed to use the measured qubit afterwards as well.
Oh, absolutely. Because it's like you're preparing it in 0 or in a known state, because you know.
So, well, in that case, you could measure them all every time, because if you measure them all and you're allowed to use this, you know what the output states are, then you could redo the circuit you've just destroyed first, right? If you measure them all, you could simply rerun the circuit you've just run to start with and destroyed. You know, like if this was measurement of all of them, you get some string of things. You put in some adaptive access to turn them all back to zeros or whatever, and then you simply plonk this back in here again.
But don't measure. No, I was thinking.
Yeah.
But you're using the qubit again, but you're using it in its after measured state.
Oh, I see. Yeah.
You can't do that. I won't get it.
Wouldn't you lose your T-gates?
Yeah, if you measure them all, then you could classically simulate it.
Yes, exactly.
State,
So
that
there
would
has
be
to
right.
be something between measuring one and measuring all, where you.
Yeah.
And I just wondered what that was, whether it was all but one, or whether it was two, or whether it was.
Yeah. Yeah, I guess that's. I'm not sure if there's a simple answer to that or not. But yeah, I guess that'd be some kind of resource issue if you're actually trying to
Yeah,
keep
yeah,
them
yeah.
Well, maybe I can have a question about this line actually. So adapting the measurements jumps you from classical simulability to full universality. Does that have any relation to what Cauchy and Conway call free will theorem? That's something, sort of says the same thing. Some actually say if quantum mechanics in the last axiom said if the experimenters are free to choose their settings, then some kind of collapse occurs. I'm not sure.
I can actually make some sort of comment on that, if you like. So when you talked about this in your talk, it reminded me of some work that Matt Pusey did whilst I was supervising him. And he showed that for any given circuit made of Clifford gates and a stabilizer, you can find a local hidden variable model for that circuit. And local means just that each system on a wire has its own hidden state. And when a gate acts, it only changes the hidden state of the wires that actually go in that gate, not any of the others. When you do a measurement, the outcome only depends on the hidden variable on that thing. And this seems puzzling at first, because you think to yourself, but hang on, we can make non-locality proofs out of Clifford things. We can make GHZ states and do non-locality arguments. So how is that consistent with what I just said? And the answer is that if you want to make a sort of non-locality argument like a GHZ proof, but sort of write the whole procedure in a circuit form, then you have to have Alice choosing to do either an X or a Y measurement. And then so if her choice is the value of a qubit, 0 or 1, then to make the non-locality argument work, you have to have a sort of X or Y measurement that is conditioned on whether this other thing is a 0 or 1. And now it's not a Clifford circuit anymore. So that's how you sort of resolve that tension with the point about. So that's the sort of the effort of the free will of the experimenters in doing a non-locality proof. If you want to model the whole thing as a circuit, makes it not be a Clifford circuit anymore. And so it's that sort of adaptivity that enables the non-locality proofs in this case. So yeah, I was reminded that as you were talking about.
But I think there are other issues with this local hidden variable idea that if you change the circuit to another circuit, the local hidden variable model that you have is, you don't use the same thing
right.
for the gates.
That's also.
Yeah, so which is a rather bizarre thing. You can just get a totally different sort of input-output stochastic relation for your gates. So it's sort of weird. sensibly.
No, it's a sort of separate one for each.
Yeah, separately.
For each circuit.
I think that's a good point to end that language again.